So welcome everyone to the Podium presentation session on the topic of data analytics and artificial intelligence. So we are going to get started. So the first presenter that we have is Cheng.
Yeah, hi guys. Can you guys hear me?
Yes. Yeah, we can hear you.
Okay, so like because of my internet, I think like I'm China, so maybe like during the presentation I will like just open the mic, and after it I will open the camera because like I'm worried about like the lag of the presentation. Yeah, so I'll share my screen now. So can you guys see it?
Yeah, we can see.
Okay, great. So I'll begin. So hi everyone, my name is Bill. I'm really happy and excited to share with you our summer research project, which is mitigating cascade failures in banking network using quantum computing. Today, I will first introduce the concept of cascade failure. Then I will talk about our project goal, the way we optimize the network structure, our motivation for using quantum solver, and some of our current results. First, why should we care about cascade failure in the banking network? And what is I will illustrate it using a really simple network that has only 3 banks, Bank A, B, and C. We'll look at their balance sheets. And let's assume that Bank B is lending $4 million to Bank A. So this loan would be an asset for Bank B and liability for Bank A. And in the same sense, Bank A is lending $6 million to Bank C. And one day, this $6 million loan comes to its maturity, and Bank C has to pay this money back to Bank A right now. But due to some reasons, maybe Bank C feels a financial shock and its asset value drops in a sudden, or its assets just not liquid enough. So Bank C cannot raise enough money to pay this debt. So Bank C goes to bankruptcy. So now Bank A cannot get this $6 million back from the crushed banks in time. But what if Bank A is actually counting on getting this money back, so it can pay back this $4 million debt to Bank B? So in the same sense, Bank A goes to bankruptcy. So now Bank B is in trouble. And if Bank B has actually liabilities to other banks or other companies, all those banks and companies will be negatively affected too. So even in this extremely simple network, we can already see the cascade. That is, this chain reaction of one bank failing leading to the other bank's failing. And if this chain reaction happens in a network containing hundreds or thousands of banks that's spanning through the whole financial system, the result of it is catastrophic. And that is what exactly happened during the 2008 global financial crisis. Following the collapse of the real estate market, some huge banks in the center of the system, like Lehman Brothers, felt the value drop in its assets and couldn't pay their debts, so they all went to bankruptcy. And with the failing of all these huge banks in the center of the banking network, all the banks connect to these banks also went to bankruptcy, and more banks were negatively affected too, and the whole network is crushed. This phenomenon is called cascade failure, and as a result of the whole banking network crushed, companies cannot borrow enough money from the bank for their daily operations. Average people worried about the safety of their money and emptied the ATM machines. And sooner or later, there's no milk in the grocery store. The whole world is asking banks to hold accountable. So in this process, we can already see that cascade failure is very severe in the banking network and is really bad for our economy. And our project goal is to mitigate them. And the main approach we took is to directly optimize the network structure, finding the best way banks connect to each other through loans or cross-holdings. And apart from this optimization, we also need to develop Python model for the banks and network object, and develop simulation for financial shocks and cascade. We developed lots of code, and we built our simulations around equations of calculating bank values in the network. Here is one example of our simulated cascade in a banking network. And we can see that this process runs naturally. It is actually a recursion function where each layer's new crushed banks will be the input to the next layer. So now I will talk about how we're going to optimize the network structure. This is the optimization model we used. The decision variable Lij here is actually the amount of money bank J lends to bank I. And this is equivalent to bank J's loss when I goes to bankruptcy. Because if J lends some money to I in a loan and I crashes, then this loan will default and J will lose this loan. It's similar to what I described in this simple example. And with this Lij being decision variable, and if we solve this whole optimization problem, we can get the optimal Lij, which is actually the optimal way banks connect to each other. Thus, using this optimization program, we're actually finding the optimal structure of the network. And with this being said, this whole inner sum here is actually the total loss of all other banks due to the I crashes. And with that being said, the whole thing that we are minimized here is actually the total loss of all other banks due to the crashes of all other banks. That is the failures in every recursion layer of our cascade simulation. So this objective function is quite nice in mitigating cascade. And the constraints here, they are just keeping some features of the banking network unchanged, such as the total liability for each bank is unchanged, and the total assets held by banks is unchanged. And we already implemented this optimization model on classical Groby solver. And I will show the result for that later. But why do we need quantum for this? So here's why. The problem lies here in this minimum operation in our objective function. This minimum operation just to make sure that each bank cannot have loss bigger than their total equity. And this minimum operation actually turns this problem into a mixed integer programming problem, which is a proven NP-hard problem. And NP-hard basically means that this problem is very complex. And the effort of solving this problem and finding the optimal solution grows drastically with the increasing number of decision variable, which is Lij here. And to make the situation even worse, this Lij is actually equals to the number of banks squared, because Lij is actually how one bank is actually the amount of loan from bank J to bank I. And because each bank can have loan to each other bank, so the total number of Lij here is actually the square of the number of banks. So with this drastic growth of the complexity of the problem due to the increase of the decision variable, we can already see that this problem is really hard to solve for a banking network that has many banks. So that's why we use quantum, because quantum lacks solving the objective function that is really hard and lacks solving NP-hard problems. So in the quantum solver or algorithm, we can treat the same classical objective function f here as a quantum Hamiltonian operator f hat. Then one combination of Lij or one set of values for those decision variable corresponds to one eigenstate of this Hamiltonian operator. There are many sets of values this decision variable can take, which is also part of the reason why this optimization is so hard. So correspondingly, there are many eigenstates of this Hamiltonian f hat. With this correspondence, the optimal solution that minimizes this objective function here is also the ground state or lowest energy state of this Hamiltonian. But here you may want to ask, why do we need to make this conversion and to work on all those states and quantum on the right, instead of just why shouldn't we just work on all the value sets on the left? Well, because there is a great phenomenon in quantum called superposition, which says that the system can not only be in one definite state, but in multiple states or superposed states all at once. So with this quantum effect added on, instead of searching for the optimal solutions one by one on the left through all the sets and finally reach the optimal solution, we can reach the whole states. We can reach the whole states and search them all at once on the right, which is far more efficient. So, and the implementation of this quantum solving process requires many complicated stuff like use of a Hamiltonian operator solely changes in time, a non-commuting operator to bring out the superposition, and almost to keep the system at almost absolute zero temperature to keep the system in the ground state, and lots of super interesting and creative stuff. But they are actually achieved by this D-wave annular in their quantum annular here. And we already connected our computer to this machine. Now we are currently in the process of converting our classical objective function to be compatible with this quantum solver, and and we hope we can get this done by the end of this month. And just to show the magic of this quantum solver, we solved some example problems and compared the time used for quantum solver and classical solver. The quantum solver time is the green dots here. And we can see that quantum solver almost took no time for problems with many different complexity. This is quantum supremacy. And we believe that this kind of supremacy will still apply for our network structure optimization problem. Finally, now I will just show some results of our current optimization done by Groby solver. So here is one huge banking network with many banks and also connections. And now we use our optimization algorithm to optimize it. And we can see that its structure has changed. And now let's apply this same optimization procedure to many networks and run cascade to see whether the cascade is mitigated or not for our optimal network. So here's the result. And in this plot, the x-axis here is just the number of initial crossed banks. And the y-axis here is the total number of failures when the simulation algorithm terminates. We can see that the optimal network always have fewer failures compared to the random one. And here is another plot. It's more interesting. And in this plot, the x-axis here is just the bank's critical value threshold. And the meaning of this threshold is this. Say, for instance, Bank A has a value of 50, and the threshold is 0.7 here. So Bank A will actually fail and goes to bankruptcy if its value drops below 35, which is the multiply of those two. And in this graph, the y-axis here is the same total number of failures. And we can see that the cascade or the huge increase of the failures happens in this phase transition point in this graph. And we can see that, the orange line, compare the orange line and the blue line here, we can see that the optimal network actually delayed this cascade happening from 0.6 to 0.65, which is quite nice. And this is just our current result. And after we make our problem compatible with the quantum solver, we're going to solve the same problem using the quantum solver, and hopefully we can plot them all together. And ideally, maybe quantum will give us better results in this result plot. But even if the result is similar, the quantum solver will still take less time compared to the classical one. So I think that's what we're going to do in this month. So thank you for listening. This is our summer research for during the summer, and we really enjoyed it. And also thank you guys for listening. And if you have any questions, so please ask. Thanks.
Okay, thank you, Cheng Chi, for your presentation. Now I would like to address the judges and ask if you have any questions. So judges, can you please unmute yourself and ask your questions?
Okay, I'll start. This is Hugh Liu, and thank you for your presentation. I just have a quick question regarding your problem formulation. You have this minimizing formula. By the way, I'd like to suggest in your presentation you may add a slide number, so that will be easier for us to refer to which slide. But perhaps it's one of those formulation. You have this LIJ. Yeah, okay, so any of those. Can you explain to me what is EJ at the denominator?
Oh yeah, the EJ is equity of the bank. Like the equity of the bank. So it's actually like the value of the bank.
Okay, so it's the loan and versus that the equity of the bank.
Yeah.
Okay, thank you.
Yes. You're welcome.
Yeah, hi, this is Ken Tallman, and I'm curious, what is holding back banks from having done this already? Is it just that this is a kind of new research area? Because it's been a number of years since 2008. Is this something that has been in the works for some time, or is this relatively new research?
I think, for instance, like the usage of the classical solver to solve this, like the similar problem is actually, I think it's been done, and we already seen some papers. Like, for instance, some papers already studied like how cascade will change with the change of the structure of the network and something like that. But the implementation of the quantum solver for directly solving the network structure, for finding the optimal structure, like we couldn't find the similar research. So that's the gap we found, and that's the niche of this research, I think.
Good, thank you.
Yeah, you're welcome.
For judges, I've included the time in the chat. You can take a look at that. I think Sauda Islam might have would have messaged you with the form, and in the form, in the notes, if they go substantially over time, you can make a note. But we do provide a 30-second buffer to account for technical issues.
Okay, so now if there are any questions from the audience, you can write them in the chat and we can go from there.
I don't think we have time for that, but there is a channel. There's a networking channel. I think it's in the moderator's guide too, Isabella, that you can go to and address the presenters specifically, and that's like open for everybody to look at answers to the questions about research.